So we will be covering Otto cycle, diesel cycle, and Joule cycle, which is also called as gas cycles. And finally, we will cover compressible flows. Just a brief idea, because when you specially go to that particular topic, you will study each and everything in detail. So we will cover the very basic idea of compressible flows. Okay, so I hope we are ready to start without any delay. Okay, so you see, basically, what happens is our real cycle, whatever like in power plant we use, or even for these in automobiles, in your petrol engine, diesel engines, what you use, these cycles are basically real cycles. Okay, now in order to do a thermodynamic analysis on those cycles, you have to assume something, you have to make some assumptions. Okay, now when you apply those assumptions to the real cycle, okay, when you apply those assumptions to the real cycle, those, and then you derive a cycle, then you derive a thermodynamic cycle that are called as air standard cycle. Again, I will tell you something. For example, you have this your reciprocating engine, okay, and there will be fluid going in, coming in, but this is your real engine. This is your real engine. Here, here maybe, for example, you will assume that you are adding heat at constant volume. You see, you assume that the piston is constant and you are adding heat in very small amount of time, but in reality this piston will be moving in real cycle. But for thermodynamic analysis, you will assume for that particular instant in which heat is added, this piston is stopped and the volume is fixed. So when you assume these kind of assumptions, what you try to do is, because if you want to analyze, okay, if you want to thermodynamically analyze the performance of any cycle, you cannot analyze the real cycle. You have to apply some assumptions, and then you can apply thermodynamic equations, and then you can analyze the performance. Okay, although after applying the assumptions, still you try that your performance that you evaluate should be as close as real cycle. Okay, of course it will not be same, but it should be as close as your real cycle. Okay, now the assumptions that we assume to convert real cycle into air standard cycles are, so first of all we assume that working fluid is ideal gas that follows ideal gas. Shivender, this is the first slide. Okay, this gets real. Okay, okay, let's go. So this is the first slide anyway. Okay, so the working fluid is assumed to be ideal gas. So now you see, look, in reality, it could not behave as an ideal gas. Okay, the pressure and temperature conditions may not be satisfied, but just for, because you do not have equations for real gases, or even if you have, still there are certain assumptions. Okay, so in order to analyze your cycles, you assume that your fluid is working as ideal gas. Now mind one thing, that fluid must be gas, it should not be liquid, and you assume ideal gas. Okay, you cannot do that, it must be gas, then only you can apply ideal gas. Okay, cycle is considered closed, and therefore mass of working fluid remains constant. Later on we will see that your gas cycle in actuality, in reality, is open, but you assume it as closed cycle, and then you do a thermodynamic analysis. Okay, now all processes constituting the cycle are reversible. So again, I am telling you, we do not have any equations for irreversible processes. So you assume that all processes are reversible, and then you do your analysis. Okay, compression and expansion, if they are happening, they are isentropic. Just 1 second. Okay. So compression and expansion processes, if they are happening in the cycle, then they are isentropic. Now, if you have combustion chamber in is assumed to be replaced by heat exchanger. If in your cycle you have combustion chamber, then what you assume is it is not combustion chamber. It is only heat exchanger. Combustion is happening somewhere else, but the heat is transferred from the combustion into the heat exchanger. Okay, you are assuming it, although in your cycles, even in your automobile cycle, in your two-wheeler or four-wheeler engines, combustion is happening inside the engine, but you do not assume combustion is happening. You assume combustion is happening outside, only the heat is added inside. Okay, and therefore if combustion is happening outside, so therefore chemical reaction is also happening outside. It is not happening inside the engine. Okay, so no chemical reaction takes place inside the engine. Heat addition and heat rejection takes place through heat exchanger. Okay, and if it is air, Cp is this, Cv is this, and gamma is this. So once you apply all these assumptions, your cycle is called as air standard cycle. Again, I am telling you, your real cycles are different from air standard cycles. Okay, your gas turbine, your Baraton cycle, your Otto cycle, diesel cycle, they are all different from air standard cycle. But for your thermodynamic analysis, you apply those assumptions and you say that now this is the air standard cycle and I can do thermodynamic analysis of on my cycle. Okay, so now we will directly from Otto cycle. Okay, now Otto cycle is basically your petrol engine cycle. These are your petrol engine cycle. Okay, now in your petrol engine cycle, there are two types of processes. What are two types of processes? Two isentropic process and two constant volume process. Okay, and as I already told you, isentropic, if compression and expansion is happening, they are isentropic, and the rest will be heat addition or heat rejection. Okay, so and we have already seen in our Carnot cycle, when we studied different cylinders from using cylinders, we saw that if look, if it is isentropic, then entropy is constant. Isentropic simply means entropy is constant, simple. Okay, and if it is compression, then what will happen? Pressure is going to increase, volume is going to decrease. Okay, and if you are doing compression, so pressure and temperature both are going to increase. Pressure and temperature both are going to increase. Then we have heat addition, but at what? Constant volume. So already we have given volume is constant, and you are adding heat, so if you are adding heat and volume is constant, so we can also say by ideal gas equation is what? PV is equals to MRT. So this is constant, this is already constant, so P by T is equals to constant. Okay, so pressure will increase and temperature will also increase to keep this ratio constant, okay, and entropy also increase. We already know entropy is equals to ds is equals to dq by t. Okay, if you are adding heat, then entropy will also increase. Okay, then expansion is opposite to compression. Okay, so entropy is constant because isentropic process, and because expansion is happening, so of course expansion means what? Pressure decrease, volume increase, pressure decrease, volume increase. If pressure is decreasing, temperature will also decrease. Finally is heat rejection, constant volume heat rejection. So constant volume means volume is constant, yes, and heat rejection is happening. If heat rejection is happening, so pressure and temperature both will decrease to keep this ratio constant. Okay, and again by this formula, if heat rejection is happening, so entropy will also decrease. Entropy will also decrease. So let us try to understand. Let us try to understand the PV and TS diagram. PV and TS diagram. How to draw PV and TS diagram for Otto cycle. Okay. Okay. So let us say this is my pressure and volume diagram, and this is my temperature and entropy diagram. Okay. So first is 1 to 2 is isentropic compression. Now I hope that you're all aware of how to draw isentropic process on PV diagram. Not isentropic process, all the processes on PV diagram and TS diagram. Because we have discussed this, we have drawn all the diagrams. Okay. So first is 1 to 2 is isentropic compression. So isentropic compression means by my volume will decrease. So if I start from here, let's say I start from here and I go something like this. I go something like this. So can I say that this is isentropic process and my pressure is increasing from P1 to P2? Yes, yes. And it is a compression process. It is a compression process. Second is, second is we are only talking about pressure and volume here. Okay, temperature and entropy we will see here in this diagram. Okay, then constant volume heat addition. How do I draw constant volume heat addition on a PV diagram? How do I draw constant volume heat addition on a PV diagram? By a vertical up. Yes, vertical up. Very nice. So this is my vertical up. So now this is 3 constant volume heat addition. Then isentropic expansion. Isentropic expansion. So it will be going in opposite direction to that of compression. Okay, like this. Okay. And then eventually I will end my cycle with constant volume heat rejection, and I already know that you all know that it is vertically downward. Okay, so this is 1 to 2, this is 1 to 2, this is 2 to 3, 3 to 4, and 4 to 1. Okay, so this is my 1 to 2 is isentropic compression. So I have to give compression work. Then constant volume heat rejection, heat addition. So I am adding heat Q in. Then turbine work, work output. Turbine work is going out 3 to 4. And finally 4 to 1 is constant volume heat rejection Q out. Q out. Okay. So this is my PV diagram. Now, TS diagram, very simple. I know that you all know that how do I draw process 1 to 2? Quickly tell me 1 to 2 process, how do I draw? 1 to 2, isentropic compression. Vertical, yes, vertical upward because temperature is increasing. Okay. So, okay. So this is 1 to 2. Then this is my T1. This is my T2. Constant volume heat addition. Temperature is increasing, entropy is also increasing. Okay. So I can draw something like this. You see, temperature is increased to T3 and entropy is also increased. This is S1 is equals to S2 and this is S3. Entropy is also increased. So this is 2 to 3. Then 3 to 4, isentropic expansion, again vertical down. Again vertical down. This one. Okay. So 3 to 4. Now entropy is same. And finally, constant volume heat rejection. Temperature is decreasing, entropy is also decreasing. So I can draw something like this. And this is my 4 to 1. 4 to 1. Again, this is my isentropic compression. This is my constant volume heat addition. This is my work of turbine or work of output. And this is my heat output, constant volume heat output. Okay. So this is basically my TS diagram. Okay. So this is your basically PV and TS diagram of Otto cycle, Now, how can I define the efficiency of Otto cycle? Next is thermal efficiency of Otto cycle. Okay. So this is my PV diagram. This is my PV diagram. I have already told you that any performance parameter, whatever it is, efficiency, may it be efficiency or COP, you always define it is as desired output upon given input. Now, what do you want? What do you want from this cycle? It is a power producing cycle. It is a power producing cycle. So, what do you want? What is the desired output? Yeah, basically network output. Network. Okay. What is network? If this is your work of compression, this is your work of turbine. So, network is equals to work of turbine minus work of compression, and this should be positive. This should be positive because what happens is whatever you are getting from turbine, some part of it is given to the compressor. Basically simple. Okay, so you want net work output. Net work should be positive. And heat input, q supplied, this q supplied heat input. Okay, now we already know that for from first law of thermodynamics, for a cycle, what is first law of thermodynamics for a cycle? What is first law of thermodynamics for a cycle? Yes, so basically q net is equals to w net. Okay, so this area also gives you q net, also gives you w net. Yes, energy that is not for a cycle, Shivandraj. That is basically in general first law of thermodynamics. That is a general form. Then we derive it for a cycle, then we derive it for the process. Okay, so I can say it is q net upon qs. So I can also write q net is q supplied minus q rejected upon q supplied. So finally, I can write my efficiency as 1 minus q rejected upon q supplied. Okay. Now, I have given you one table, a very good table I have given you, and I have shown you how to calculate heat rejection or heat transfer in constant volume process. So can you tell me quickly, constant volume process, how can I find out heat transfer? What is QR and what is QC? What is QR and what is QC? Constant volume heat transfer in constant volume process. How do you find out? Okay, if you don't remember, let me know if you now remember. MCV. This is rejection. Okay, so this is rejection. 4 to 1. So I can write T4 minus T1. Okay, and supplied is MCV T3 minus T2. Do you remember these formulas? We use CV here for constant volume. We use CP for constant pressure. CP for constant pressure. Okay. So I can, because it is air, I know it is air, and the same fluid is flowing there. Fluid is not going out. Same fluid is flowing. So mass is constant. CV is also same. I can write 1 minus T4 minus T1 upon T3 minus T2. Now I can take out T1 and I can say T4 by T1 minus 1, and I can also take out T2 and I can say T3 by T2 minus 1. Okay, so right now this is my efficiency. So what do I get? Efficiency is equals to 1 minus, I have taken out T1 and here I have T2, and what do I have here in the numerator? T4 by T1 minus 1, and this is T3 by T2 minus 1. Okay, this much is okay? Yes, T3 by T2 minus 1. Yes, okay. Now we will simplify it in the form that is mostly used. Okay, so you see here, let me take this diagram. Yeah. Okay, let's take us to next page. Now, what is the efficiency that I got? Efficiency is equals to 1 minus T1 by T2, and here we have T4 by T1 minus 1, and here we have T3 by T2 minus 1. Okay. Now, tell me what is process 1 to 2? Process 1 to 2, what is this? It is isentropic process. Isentropic process. An isentropic process, I can write T2 by T1 is equals to V1 by V2 gamma minus 1. Gamma minus 1. Okay. And I can also write process 3 to 4, again isentropic expansion, and I can write T3 by T4 equals to V4 by V3 gamma minus 1 by gamma. Okay, now can you also go back to this diagram, and can we say that V2 is equals to V3? V2 is equals to V3 and V4 is equals to V1. Yes, V2 is equals to V3 and V4 is equals to V1. Yes, right? V2 is equals to V3. You see, same volume. And V4 is equals to V1. So can I write V1 by V2 gamma minus 1 by gamma? Yes. So basically, you see, T2 by T is equals to V2 by V1 by V2 gamma minus 1. I'm sorry. This is also same. Okay. So, and T3 by T4 is also V1 by V2 gamma minus 1. So, by A and B, can I write T2 by T1 is equals to T3 by T4? Yes. और थोड़ा सा like I'll change it a little bit and can I write T4 by T1 is equals to T3 by T2? I can write this. थोड़ा सा I have modified it. I have taken it the other side. So I have written T4 by T1 is equals to T3 by T2. Yes. Now let me subtract minus 1 here, minus 1 here. They're also equal. So I was trying to cancel this. I have gotten T1 by T2. Efficiency is equals to T1 by T2. Efficiency is equals to T1 by T2. Okay. Now, there are few terms that you need to know. There are few terms that you need to know. Uh, just 1 second. I did not want it to do this. Okay. Anyway, now, so basically, this is what you got. What efficiency is equals to? Hmm, efficiency is equals to 1 minus T1 by T2. I mean, the pages are a little bit shuffled. Okay. So this is how we started in the beginning. And there is this middle page here. And then next this. Okay. So just try to be a little cautious when you study. Now, the efficiency we have gotten 1 minus T1 by T2. T1 by T2. Okay, got it? Now, this T1 by T2 is basically, you see how your engine works, how your uh, petrol or diesel engine is there. So it's something like this. Okay, somehow it looks like this. Now piston only, this is the whole volume. Okay, this is V1, this is the whole volume available, this is the whole volume available, this is your V1. Okay, because piston is here and all the volume that is available is V1. Now piston only moves, piston only moves till this point, till the point 2. This is 1, this is 2. Piston only moves to point 2. Okay, this volume is called as swept volume. Why? This is the volume that is swept by the piston. Piston only moves till here. It does not go further than this. Why? Because these valves, these are inlet valve and exhaust valve through which fuel or air comes in or the mixture comes in. Okay, so the piston does not move till the end, till the very end. It does not move till here. Why? Because every time it is going to hit the valve. So this is the clearance space that is given to the valve. Yes, that is the clearance space that is given for the valve activity. Okay, so this volume is called as clearance volume. This is called as clearance volume. Okay, and this V1 by V2, V1 by V2 by this is V2 as well, right? This is V2 as well. This is the volume now available at point 2. Okay, so this is called as V2 is equals to clearance volume, and this is called swept volume. Now this ratio before the compression. Now this is, you see, this is before compression. Piston is here before compression. Then when the compression ends, piston is here after compression. So the volume before compression and the volume after compression is called as compression ratio. So this is V1 by V2. V1 by V2. Okay. And that is also equal to, you see, V1 by V2. So I can say that T2 by T1 is equals to V1 by V2 gamma minus 1 or compression ratio gamma minus 1. Compression ratio gamma minus 1. So how can I write my efficiency formula? I can write efficiency is equals to 1 upon 1 by R gamma minus 1. This is how I can write my efficiency formula in terms of compression ratio. In terms of, and why compression ratio is important? Because in question they will give you compression ratio most of the time. Otherwise, you will need to find out. So compression ratio term is very important when we talk about Otto cycle or diesel cycle. Okay, clear? Quickly. Look, this is compression ratio, right? This is compression ratio. And it basically tells you volume before. So now you see, when piston is here, so this whole volume is available with the cylinder. Okay. Now after compression, piston reaches at this point. After compression, piston will reach here. So what is the volume that is available in the engine, in the cylinder? Only this volume, only this volume. So it is volume before compression divided by volume after compression. Okay, that's it. And then piston moves this side, so expansion happens. Piston moves this side to expansion happens. Okay. So basically what is happening, you see, from 1 to 2, piston has moved to compression. And then when piston reaches at this point 2, you will add heat Q in at constant volume. And then piston will move this side and expansion will happen till it reaches back here. And when it reaches here, then you will reject heat Q out. So these are the four processes that are happening here. Okay. Chalo, tell me quickly, then we will move ahead. Okay. So efficiency, now I know. Efficiency I can write once either T1 by T2 or 1 upon 1 minus R gamma minus 1. So these are the formula that we will be using very frequently. Now, next is work output of Otto cycle. So in this cycle, if I need to find out network, so I can do work 1 to 2 plus work 2 to 3 plus work 3 to 4 plus work 4 to 1. This slide. Yeah, this is the start of the derivation, no? Okay, just 1 second. Okay, this is the start of the derivation. So let me write the numbers. This is your first slide. This is your second slide. Then this is your third slide. Okay. And finally, we have reached here. Got it? Chalo. So I will not waste much time because we all know that constant volume work is how much? Constant volume work is how much? Yes. So when constant volume work is how much? Zero, then this is zero and this is zero. Okay. And this is isentropic. These two are isentropic process. Isentropic process. So I hope you already know how to calculate isentropic work transfer. It is P3 work 1 to 2. 1 to 2. Okay. So 1 to 2 is, let me write 3 to 4 first because it is work output. Okay. So let me write, because it is negative work. It is work output, so it will be negative. I'll write later on. So P3 V3 minus P4 V4 by gamma minus 1. This is this. Okay. Now minus P2 V2 minus P1 V1 upon gamma minus 1. Okay. Now again, these are both isentropic processes. They are both isentropic processes. So I can write process 1 to 2 P2 by P1 is equals to V1 by V2 gamma. So basically R gamma. Okay. What about process 3 to 4? P3 by P4 is equals to V4 by V3 gamma. So that is also R gamma. So from A and B, I can say P3 by P2 is equals to P4 by P1. And this is also called as pressure ratio. This is also called as pressure ratio. Okay, RP. First derivation, which one? So Did you take the screenshot? This is no. This is the first slide. This is the first slide, right? Okay. So I can say this. And I can also say, look, V1 by V2 is equals to R. So V1 is equals to R V2. Also, V4 by V3 is equals to R. So V4 is equals to R V3. It's okay, Shivendra. Now, why I am doing this? I am just trying to simplify my equation, and this equation you will use very rarely, very rarely. Okay, so even if you use a, and I am doing basic mathematics, simple. Okay, so even if you don't understand my, it's fine because 99% of the time you will not understand, you will not use it. Okay, but because we need it later on, that's why I have to do it. Next, so I can take network is equals to, let me take P1 V1 upon gamma minus 1 out, and I 3 upon P1 V1. I will divide everything by P1 V1, okay? Minus P4 V4 upon P1 V1 minus P2 V2 upon P1 V1 plus 1. Now you see, look, P, this is P1, okay, P3 by P1. P2 by P1 is given P4 by P1, P3 by P1. Okay. So now what do you have? You see, you have V1, you have V3. Okay. You have P4 by P1. Just 1 second. Let me see what we have done here. So we have divided P1 by V1, everything. Okay. This much is clear. No. That is okay. 3 by 4, I think, process 3 to 4, that is okay because these are always inversely proportional. If it is P3 by P4, then it is V4 by V3. That is okay. If you write P4 by P3, then volume will be V3 by V5. Okay. That is not an issue. The thing that you are going to do here is basically we have to substitute V4 in terms of V3 and V1 in terms of V2. Okay. Also, we have to substitute P3 in terms of RP P2. Okay. So wherever you have P3, you will substitute RP into P2 and P4 is equals to RP into P1. Okay. So basically you have to substitute all the values of pressure and volume using these four equations. Okay. C and D. Okay. I am not doing this. I am not doing this. I will just give you what you will get in the end. And trust me, you will not. I mean, this derivation is really not important. That's why I'm skipping the steps. Okay. So you will get RP minus 1, and again compression ratio gamma minus 1 by this. Okay, so this is your net work. This is your net work. Very rarely you are going to use this equation. We will use general equations. General equations is what? These equations. These equations we will use if we need to calculate work, net work. Okay. So net work is given by this equation. Now, why I did that is basically I need to find out mean effective pressure for Otto cycle. So mean effective pressure is given by net work upon swept volume. Swept volume. As I said, what is swept volume? Look, this is V1, this is V2 till here, and this is your swept volume. So swept volume is basically V1 minus V2. V1 minus V2. So swept volume is equals to V1 minus V2. Now from this equation, you see what is V2? V2 is equals to V1 is equals to RV2. Okay. So I can write V1 minus R. Sorry, V1 is equals to RV2, right? V1 is equals to RV2. Okay. So I can write R V2 minus V2. Yes. So V2 is equals to R minus 1. Sorry, into R minus 1. This is your swept volume. Okay. Now, I already got my equation earlier. What was that? P1 V1 upon gamma minus 1 RP minus 1 R gamma minus 1 by gamma. And what is swept volume? V2 R minus 1. R minus 1. So if you write here, you see what is there? P1 is there. Okay. And RP minus 1 is there. R gamma minus 1 is there. Let me take this gamma minus 1 here and R minus 1. Okay. Now what is left? This V1 and this V2 is left. So V1 by V2, and that is equals to R. R is what? V1 by V2. So this is your mean effective pressure. This is your mean effective pressure. Again, from derivation point of view, it is important if you are in university or something, if you have to still give your semester exam, or you are taking ESC. But for GATE, derivation is not important. This formula is more important, but if you know this formula, you can easily derive this. Okay. Again, 99% of the time we will use our general formula this, and we will start from here and we will solve questions. Very rarely, just 1%, let us say 5% of the time, you will need this formula anyway. Okay. Yes, I know. I was, like when I was writing it, even I thought so. Let me replace gamma with different color. Okay. So this is basically gamma and this is gamma. That's all. Everything else is R. Okay. Everything else is R. This is gamma. Okay. So let us solve a quick question on Otto cycle. I should not start diesel cycle so soon because like chalo, we'll do one question. Maybe you will understand what type of questions. And again, look, it will be a big question. It is from a book, not from GATE or any exam, but it will cover more than one concept. So basically, whatever we have done, it will be clear to you. Okay, so just be patient with me. Okay, chalo. In a Otto cycle, air at 17 degrees Celsius and 1 bar is compressed adiabatically. So in the compressor, it is entering. Okay. So what is compression is starting? 1 point is starting. So T1 is equals to 17 degrees Celsius, or I can say 290 Kelvin. At what pressure? 1 bar. 1 bar means 10 to the power 2 kilopascal. And it is compressed till the pressure becomes 15. So, yani compressor outlet is P2. This is compressor inlet P1. Okay. P3. Okay. Compressor outlet yani ki P2 is 15 into 10 to the power 2 kilopascal. Heat is added at constant volume until the pressure rises. That means final pressure after heat addition, which is P3, is 40 into 10 to the power 2 kilopascal. What I need to find out? I need to find out Otto cycle efficiency. I need to find out compression ratio, which is V1 by V2, and mean effective pressure, which is net work by swept volume. Okay, chalo. So efficiency, first thing efficiency. Efficiency of Otto cycle is given as 1 minus 1 upon R gamma minus 1. No, I don't know I don't know R. Okay, I don't know R. Let me just 1 second. Let me R gamma minus 1. I will try my best not to get R and gamma same, but okay. So R is what? R is what? R is equals to V1 by V2. V1 by V2. I don't know R. R is not given in question. So but I need to find out R. How can I find out R? So you see, what is process 1 to 2? It is isentropic, okay, which is what? PV gamma is equals to constant. So can I say P1 V1 gamma is equals to P2 V2 gamma? Yes. So R is what? R is V1 by V2 is equals to P2 by P1 1 by gamma. Okay. Now I know P2 is 15 and into 10 to power 2, and this is 1 into 10 to power 2. 10 to power 2 will get cancelled, and this is 1.4. This is 1.4. Okay. So R, when you calculate, you will get 6.2. Now I can substitute my R here, and I can find out efficiency 1 minus 1.4 minus 1. Here this is around 0.538. So basically 53.8% efficiency you have gotten. Okay, this much is fine. Yes, it's very simple. Till now it's very simple. Okay, now the next we have to find out mean effective pressure. We have to find out mean effective pressure. So what is mean effective pressure for Otto cycle? Mean effective pressure. By mean effective pressure is equals to net work by swept volume. By swept volume, yes. So what is swept volume? By swept volume is V1 minus V2. How can I find out V1, V2? By you see, you know this at one point. First of all, I know it is air, so I can apply ideal gas equation. So can I say P1 V is equals to RT. This is small v, okay? Small v is equals to capital B by mass, okay? RT. So it's V1. I can say RT1 by P1. Can I say this? Yes or no? Yes. Similarly, I can find out V2 as well here. Okay. So V1 is equals to R T1 upon P1. So what is R? R is gas constant. R is gas constant. Now tell me, can I take this R? Yes. Can I take this R? Yes, I cannot take this R. This is universal gas constant. I need to find out my specific gas constant, which is divided by molecular weight. So 8.29 kilojoule per kg Kelvin. Okay, which I think is 0.287 kilojoule per kg Kelvin. Okay, so R is 0.287. Temperature दिया हुआ है at the beginning and pressure is 10 to the power 2. So this you will get 0.8323 meter cube per kg. Similarly, I can find out specific volume at point 2 as well. 2 upon T2. Now the problem here is I do not know T2. Can you tell me how can I find out T2? Can you tell me how can I find out T2? Yes, by basically ideal gas equation for isentropic process. You see, 1 to 2 is isentropic process. So I can write for this process, I can write T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. Yes, from volume also I can find out, but I do not know V2, right? First of all, I need to find out V2. Or maybe compression ratio also I can find out. Yes, I know R. I know R. Okay, so from there I can find out. Yes, that is correct. Okay. Now, I mean, I don't know individual volumes, but I know pressure ratio. But I know compression ratio. Okay. So let me take T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. So from here, T2 is equals to T1. T1 is what 290. T2 is what 15. This is 1. 1.4 minus 1 by 1.4. So it's basically 629. So I know T2 as well, 629. So now this is 0.12034 meter cube per kg. So now by these two equations, I can find out my swept volume. Also, it is called as stroke volume, okay? Because piston has moved one stroke. It is also called as stroke volume or swept volume. So V1 minus V2 is equals to 712 meter cube per kg. Okay. So now I know this, but I still don't know this. I still don't know this. How can I find out this? Anyone? I can use my long formula. That formula that we derived, that is one way. The other ways, I can use my efficiency as well by what is the general definition of efficiency? Net work by heat supplied. Net work by heat supplied. Now efficiency I have already defined. It is 0.538. Net work I don't know. but I need to find out this QS. Okay, so heat supplied, what is the heat supplied in this? Heat supplied at constant volume, I have already defined this for you earlier. It is mCV dt, and dt is what? T3 minus T2. Okay, now this is m, I can take as 1 because why? I can take the numerator as kilojoule per kg and denominator also kilojoule per kg. So I can remove this. Only CV. Okay. Now CV is given as, CV is this. CV is given as this. I know T2 also. I have calculated T2 here. Where? Here. T3 I don't know. T3 I don't know. Now how do I calculate T3? How do I calculate T3? I can use my ideal gas equation. Anyone? What equation I can use to calculate T3? By process 2 to 3 is constant volume. So I can say P3 by P2 is equals to T3 by T2. So basically T3 is equals to T2 into P3 by P2. You see, I know T2, T2 is this. I know P3, P3 is this, P2 is this. Very simple, very simple. When you put all the formulas, all the values, you will get T3. I know it got a little congested, but I just want to do it here so that, okay, so this is your T3. Now I can write here. Okay, let me add to another page. So my efficiency is equals to net work, actually small and CV T3 minus T2. Efficiency is 0.538. Net work I need to calculate. CV is given 0.717 and T3 I have just calculated, and this is 629. So net work I have gotten 404.92 kilojoule per kg. So now I can substitute 404.92 kilojoule per kg upon, this is 0.712 meter cube per kg. So this and this will get cancelled and you will get 568.7 kilojoule per meter cube, which is also what? Kilopascal. Okay. I hope that you know that this is also kilopascal. Okay. Why? By kilojoule per meter cube is what? Joule is what? Joule is Newton meter. Okay. And this is meter cube. So meter and meter gets cancelled. Kilo Newton per meter square. What is Newton per meter square? Pascal. So this is also kilopascal. Okay. So your mean effective pressure is this. So this is one question on Otto cycle. Okay, I tried to cover everything in one question. Okay, and again in GATE you will not get these big questions. It is from a book. So in books you will, I mean basically more than one concept. Now this is covering three concepts. Actually more than three concepts. You have applied ideal gas equations. Okay, you have applied this ideal gas equation, and for processes also you have applied isentropic process, constant volume process. You have used efficiency formula, compression ratio you have defined. So more than 3-4 concepts we have covered. Got it? Yeah, it's basic physics. I think it's not an engineering, like even engineering level. It's basically your universal gas constant value is 8.314 kilojoule per kilomole Kelvin. Okay. And when you use this in ideal gas, PV is equals to N R T. So this is number of moles, and this is universal gas Even I covered this when I, when I talked briefly about ideal gas equations. Okay. Now this equation is not used by mechanical or aeronautical engineers. It is used for chemical engineers. Okay. Because here we're talking about number of moles. Now in order to convert that into mass, now the other equation that we use is PV is equals to MRT. PV is equals to MRT. Okay. So here what we do, here R is equals to, here R is equals to R bar by molecular mass. Yes, and N is equals to M by molecular weight. Same molecular mass or molecular weight. Okay, so basically we just turn it into that. Okay, so this is how you, now this R is your specific gas constant. Specific gas constant. Why? Because when your gas will change, its molecular mass or molecular weight will change, and therefore this value will change. This will always remain constant. This will always remain constant. Its value is fixed. This value is fixed. Okay. So you can write this as, in this equation, PV, you can write N as mass upon molecular mass. You can write this as specific gas constant into molecular mass and T. So this will get cancelled and you will get PV is equals to MRT. Okay, got it? Chalo. Okay, now let's go to diesel cycle. Now, diesel cycle is same as Otto cycle. There are few differences. First is, here, look, 1 to 2, 1 second, is isentropic compression, same as Otto cycle. 3 to 4 is isentropic expansion, same as Otto cycle. 4 to 1 is constant volume heat rejection, same as Otto cycle. The only difference here is you add heat at constant pressure, and therefore it is also called as constant pressure cycle, while Otto cycle is called as constant volume cycle. Constant volume cycle. So I hope that TS and PV diagram, drawing TS and PV diagram will be very easy for this, and for me also explaining will be much easier. Okay. So this is, let us say, PV diagram, TS diagram. So same, last will be constant pressure or volume. Which last? No, this is constant volume. Heat rejection, right? Constant volume. Only difference is heat, how you are adding heat. That's all. Okay. So see, first process, let me draw same. What we did there, I will draw same. Okay. And I will draw this also. And let me draw this also. Okay. Now, okay, wait. So basically, this was your Otto cycle. This was your Otto cycle. Okay. This is 1, 2, 3, 4. This was your Otto cycle. Similarly, here, This was your Otto cycle. 1, 2, 3, 4. Okay. Now, diesel cycle, the only difference is you add heat at constant pressure. You add heat at constant pressure. So instead of vertical line, what kind of line I need to draw? Instead of vertical line, what kind of line I need to draw? Horizontal line. Yes. So instead of this, I will draw this line. I will draw this line. Okay. So now my cycle is 1 to 2, 2 to 3, 3 to 4, like this. Okay. So basically this is not there anymore. It's like this. Okay. So this is my constant Q in, constant pressure. This is work input, work output, heat rejection. Okay. Now how can I might change my TS diagram quickly? How can I change my TS diagram? Which slope is higher? Which slope is higher? Constant volume or constant pressure? Which slope is higher? Yes. So basically, this is my constant volume. My constant pressure will have a little lesser slope like this. That's all. I mean, if I draw directly, you will not even notice this. But just so I want to tell you that how will this matter? How will this differ? That's all. So this is my constant pressure line. Slope will be little less. Okay. So here, this is my Q in. I'm sorry. This is my work input because it is isentropic compression. Okay. This is my Q in, constant pressure. This is constant volume heat rejection. And this is W output. Okay. Yes, that is correct. Volume will have a higher slope. Okay. So these are your TS and PV diagram for your diesel cycle. Now, how do you calculate thermal efficiency? How do you calculate thermal efficiency? We will start from the basics. Thermal efficiency is equals to net work by Q supplied. Q supplied. Okay. I know that from first law of thermodynamics, Q net is equals W net. So Q supplied minus Q rejected upon Q supplied, 1 minus Q rejected upon Q supplied. Okay. Now rejection is happening at constant volume. So I can write M CV T4 minus T1. But supplied is happening at constant pressure. So what should I write? What should I write? Constant pressure. Remember? M what? CP. Yes. T3 minus T2. Mass and mass will get cancelled. 1 upon 1 by gamma. By gamma is what? Cp by Cv. Okay. T4 minus T1 upon T3 by T2. Okay. Now I need to further simplify it. So what is 1 to 2 process? 1 to 2 is isentropic. So I can write T2 by T1 is equals to V1 by V2 gamma minus 1. Okay. And this is also equal to R gamma minus 1. Okay. So T2 is equals to T1 R gamma minus 1. Okay. Now there is one thing before we move ahead. I need to tell you is what happens. Do you know what is the difference between auto and petrol and diesel engine? Petrol and diesel engine. Do you like in general? Do you know in terms of fuel? In terms of fuel. No, that is okay. That is okay. So you usually what happens is let me go back and okay. So in petrol engine, before the engine we have a carburetor. Okay, we have a carburetor and fuel fuel and air is properly atomized and mixed. Yes, yes, that is all okay. Ignition will be different. Yes, ignite with diesel fuel. That is all okay. But in terms of fuel mixing, I wanted to tell you. So here fuel is coming, air is coming. So here fuel and air is properly mixed, and here mixture goes out. Mixture of what? Fuel and air. And this mixture of air goes inside the engine. Okay, mixture of air, and here you have ignition plug, spark plug, which is also you could say. Okay, so you provide a spark to burn this mixture. Okay, and then out goes, when goes out it goes exhaust gases. Okay, but in diesel engine what happens is directly comes in air comes in and air is compressed. So fluid piston is here, air is coming in, then air is compressed. So when the piston is here, the very compressed air is here at very high temperature and pressure. Now we have a fuel injector here. We have a fuel injector here. Okay. So look, this is 1 to 2 process, compression process. Then 2 to 3 is what? You at 2, when piston reaches here, you start fuel injection. And at point 3, which is also here, you stop fuel injection. Okay, so basically you start injection fuel, you stop fuel injection, and that is called as cut-off point. When you stop the fuel injection, it is called as cut-off point. It is called as cut-off point. Okay, so that is what is happening here. 1 to 2 is what? 1 to 2 is compression. 1 to 2 is air compression here. Only air is compressed. Now at this point, fuel is start entering inside. Fuel is start entering inside. And combustion is also started. Combustion is also started. You see, this air is very high temperature and pressure. So as soon as fuel has entered inside, it starts burning. So if it starts burning, what happens? It start pushing the piston down. Okay, and heat is added. Basically temperature and pressure will rise further. So basically you are adding heat due to combustion. Okay, and combustion is happening, fuel is also injected. Now fuel is stopped injecting at point 3. Okay, so this is called as cut off point. This is called as cut off point. 3 is cut off point. Okay, now this is what? This is V2 is equals to clearance volume. Okay, and this whole is V1, and this is called as swept volume, which is V1 minus V2. Okay, now let's go to process 2 to 3. 2 to 3 is what? Isobaric, constant pressure. So I can say V3 by V2 is equals to T3 by T2. And this ratio is called as cut-off ratio. This RC is called as cut-off ratio. V3 by V2 is cut-off ratio. So volume after cutoff and divide by volume before cutoff. And this is, so RC is equals to T3 by T2. So I can say T3 is equals to T2 RC. Now what is T2? T2 is this. So T3 is equals to T1 R gamma minus 1 into RC. Okay. Now we need, okay. So you see what we have? We have find out, you see here in this equation, T1 we have, T2 we have found out in terms of T1 R gamma minus 1. T3 also we have found out in terms of T1. Now what is left? T4 is left. So I will go to process 3 to 4. So now process 3 to 4, which is again isentropic. Okay. So this is T4 by T3 is equals to V3 by V4 gamma minus 1. Okay. I write V3 by V2 into V2 by V4. Yes, gamma minus 1. Now what is V3 by V2? What is V3 by V2? It is RC. And you see V4, from here you can find out that V4 is also equal to V1. Okay. So can I write T4 by T3 is equals to V3 by V2 into V2 by V1 gamma minus 1, which is also equal to, now this is basically cutoff ratio, this is compression ratio, this is 1 by compression ratio, 1 by compression, RC by R gamma minus 1. So now I got T4 is equals to T3 RC by R gamma minus 1. Now T3 I know from here what is this. So I can write T1 R gamma minus 1 RC into RC gamma minus 1 by R. Okay. So if I simplify this, you see this and this will get cancelled and T4 is equals to T1 RC gamma. So T4 is equals to T1 RC gamma. Okay. Now I got everything. I got everything. Now I am not going to substitute this in your equation. Okay. What is my equation? 1 by gamma T4 minus T1 upon T3 minus T2. I am not substituting it. You have to substitute T4, T3, T2 and T1 as it is. Okay. And you will get 1 upon 1 minus R gamma minus 1. Now what is this? This is Otto cycle efficiency. But in addition to this, you will get something else, which is upon cutoff ratio gamma minus 1, here gamma cutoff ratio minus 1. So this is basically your efficiency for diesel cycle. This is your efficiency for diesel. I know it is little big formula, but if you do 4 5 numericals on this, it's very easy. Diesel cycle efficiency. Diesel cycle efficiency. Okay, got it? It's look, it's simple derivation. I have not done anything new. I have only used my equations that I have taught you and a simple mathematics. All these equations, ideal gas equations, how to calculate heat transfer in constant volume, constant pressure. This is gamma, this is gamma, this is RC, this is gamma. R is only here. This is gamma and this is gamma and this is gamma. 3 gamma. Okay. Now we have to again do the tedious thing of work output. Again, I am not going to do this because very rarely you are going to use this. Work 1 to 2 plus work 2 to 3 plus work 3 to 4 plus work 4 to 1. Now look, 4 to 1 is 0, I know, and you also know. Okay, ठीक है. I mean, I have, for now, I have, okay, just 1 second. For now, I have marked it with a different color. I'll try to, like maybe make it italic, but I really don't know how it will make a difference. Let's see, I mean. Okay. So 4 to 1 is 0. 4 to 1 is 0, we all know. Now, what is 1 to 2? It is 1 to 2 is what? Compression. So it is what? Minus P2 V2 minus P1 V1 upon gamma minus 1. 2 to 3 is what? Constant pressure. So P2 V2 minus V3 minus V2, final minus initial. Plus what about 3 to 4? 3 to 4 is P3 V3 minus P4 V4 upon gamma minus 1. Okay. Alpha to indicate R. Look, I can use alpha, but basically even in books and all you will get R. Okay, so look, I'm really telling you it's not much. If you revise it one more time and you write it yourself when you revise, right? When you revise again and you write yourself, then maybe try to be little cautious. But really, it is not too much. If you just revise it once or twice, you will know what is R, what is gamma. Seriously. Okay. So, I mean, it's not very difficult. I know it can be little difficult at this point of time. You will get confused, but once you solve 2 3 questions, it will be very easy. You will be able to differentiate between where is gamma, where is R. Anyway, okay. Chalo. Now again, I am not solving again the same thing. You have to do what we did there. Okay. So man, we have to calculate P3. Everything we need to calculate in terms of RP, RC, and all that. Okay. I am giving you the last formula which you will get because derivation is really not important. I just wanted to do it there so that you will get some idea. Okay, network P1 V1 gamma minus 1. Now, okay, this is gamma, this is gamma. Okay, now R, okay, R gamma minus 1. Then you will get gamma RC minus 1 minus R 1 minus gamma RC gamma. I have written down this equation. Even I can't remember it seriously. RC minus 1. Okay. So this is basically your equation. Again, I don't think you're going to ever use this, but just I'm giving you. Okay. And similarly, you can find out mean effective pressure. So P mean is equals to net work output by stroke volume, and the same first bracket is there. Which bracket? Which bracket? After gamma, which one are you saying? RC minus 1. Yes, bracket is there, no? This one. Yeah, there is bracket here. This one, no? It is multiplied by RC. Gamma is multiplied by RC. Okay. No, it's, I mean, it just, it, because they are big brackets. So don't get confused. Okay. It's the same. Okay. I mean, because they were big brackets, that's why I draw a square. It doesn't have any significance in circular and square. Okay. They're all same. Now, this we already know, like we have V1 here, and this is basically V2 R minus 1. Okay. So same thing what we did there, we'll do here. P1 gamma R gamma. I mean, I really don't know what to do here, but it just, this is how it is going to go. Gamma R C minus 1 minus R RC gamma minus 1, then bracket closed upon, this is gamma, okay? Gamma minus 1 R minus 1. Okay? It's okay. I mean, don't worry about it much. If it would have been very important, I would not have left it like this. Okay, but because you keep asking, because you keep seeing terms mean effective pressure and all these terms, that's why I wanted to mention it before we go to any question. Okay, now, so what is the difference? In auto we use a spark plug, as I told you. In fuel it is self ignition. How do ignition happens? In auto cycle we use a spark plug. In diesel cycle self ignition happens because of high temperature and pressure. Okay, compression ratio, very high compression ratio in diesel compared to auto cycle. So diesel we have 16 to 22. Speed high, low. Torque is opposite, low and high. Heat addition, only heat addition process is different. Here constant volume, here constant pressure. Okay, so I hope this is okay for now. Let us do one question on this diesel cycle. Okay, okay. Determine the ideal efficiency of the diesel engine having a cylinder with bore. So look, diameter is 250 millimeter. Bore means diameter. Okay. Stroke length is 375 millimeter. Clearance volume is 1500 cubic centimeter cube. And they are saying fuel cutoff occurs at 5% of the stroke. So cutoff happens, this cutoff, yani कि this point V3 is at 0.05 of the total stroke volume or swept volume. Okay, assume gamma as this. Efficiency I need to find out. By efficiency, simple formula I have given you, 1 upon 1 minus R gamma minus 1. This is for Otto cycle, simple. For diesel cycle, you will add something more. So this is cutoff ratio, gamma minus 1 and gamma RC minus 1. Now, what is RC? RC is equals to V3 by V2. Volume before cutoff, volume after cutoff. Okay. Now, I know V2. What is V2? By V2 is this clearance volume. So, V2 I know. V2 I know. But I don't know V3. I don't know V3. So how do I find out V3? They have given cutoff volume. So cutoff volume is what? You see this. This is your cutoff volume, this part. So this is what? V3 minus V2 is equals to 0.05 of swept volume. Swept volume. But swept volume is not known. How do I find out swept volume? Anyone? How do I find out swept volume if diameter and length is given? Anyone, any idea? Swept volume. You see this cylinder. You see this cylinder. This cylinder. I need to find out this. Yes. Swept volume, I'm saying swept or stroke volume. So it is by this is the volume that is swept. So this is what? By this piston is circular, right? So pi by 4 d square into L. Pi by 4 d square into L. L is this length. This is stroke length or swept length. This length is stroke length. Yes. Area. Yes, area into length. Area is what? Pi by 4 d square into length. Okay. So swept volume is pi by 4 d square is 0.25 a square into length 0.375. So swept volume is basically 0.0184 meter cube, or I can say 18408 centimeter cube. Okay, so V3 minus what is V2? 1500, 0.05 into 1840. So V3 you will get 2420.3 centimeter cube. Now I can find out my RC. RC is 2420.3 by 1500 is equals to 1.6135. Now I know RC, I know gamma. I don't know R. I don't know R. How can I find out R? By R is equal to V1 by V2. Now what is V1? What is V1? V1 is, can I say it is swept volume plus clearance volume? Yes. And that is clearance volume. So it is 1 plus swept upon clear. Any doubt, anyone in this variation? By this is my swept volume. This is my clearance volume. And total is what? Total is V1. Anyone, any doubt in this particular format? Now this is 18408 and this is 1500. So this is 13.27 centimeter. Cutoff ratio gives you, okay, look, where is compression happening? Compression is happening from 1 to 2. Okay, so compression ratio is R, which gives you volume before compression and volume after compression. Compression ratio gives you volume by 1 to 2, it is happening, right? So volume before compression by volume after compression. Cutoff ratio basically signifies when the fuel has cut off. When the fuel is cut off. Now where is it happening? Is it happening? It is happening from 2 to 3. So it is volume after cutoff V3 by volume before cutoff V2. Okay. Cutoff of what? Cutoff of fuel. Cutoff of fuel. Okay. Okay. So now I have everything. Now I can put it into my formula. So let me put it here. Efficiency is equals to 1 minus 1 upon 13.27. Now gamma is 1.4 minus 1, it is 0.4. Okay. RC is 1.6135. 1.4 minus 1 upon 1.4, 1.6135 minus 1. So if you solve this, efficiency you will get 0.6052, which is 60.52%. Okay, 60.52%. Okay, got it? Yes, you have to be with me because I think we will go to 11:30 today. Maybe little we have to extend. Okay, so just be with me and let's finish it today itself. Okay, otherwise I have to take one more class again for 1 hour or something. Let's not do this. We'll finish it today. Now two topics: Otto and diesel cycle is done. We will move to now Joule cycle. Joule cycle. Okay. So basically, they're also called as gas cycles. These are Joule cycles are also called as gas cycles. Okay. Now there are two types of cycles: open cycle and closed cycle. Now, what is open cycle? Open cycle is basically, you see, it is open to atmosphere. If you have this compressor, now this compressor takes fresh air every time. It takes fresh air. Okay, so one, then fresh air is compressed, two, and then it is combustion chamber. So basically it has some fuel here. Fuel is burned. Now this is fuel, it is burned, and it basically, now this is air. This is mass of air. Okay, this air is heated by this fuel burning. Okay, so Q is supplied, Q in, and then it goes out, mass of air at very high temperature and pressure goes out, and then we use a turbine here, we take out work output, and then it is again left to the, so this is 3, this is 4, then it is again left to the surrounding. And this is basically what we use 98 to 99% of the time in real scenarios. But basically, look, we cannot do thermodynamic analysis in this cycle. Okay, you see, we assume that, one second, we assume that cycle must be closed. Okay, no chemical reaction must happen. Now in combustion chamber, what is happening? Chemical reaction is happening. So that is the reason we do not assume, we do not do any analysis on this. We assume a closed cycle. How do we close it? Same thing. What do? We use this compressor. Air comes in, air is compressed 1 to 2. Okay, so you have to work, you have to provide work. Now instead of combustion chamber, we assume we have a heat exchanger. Now whatever combustion is happening here, we say combustion is happening somewhere else, only heat is supplied, only heat is supplied. So this is the heat exchanger here in our in an air standard cycle. Okay, and then this air comes to the turbine, and then we assume that this is basically joined together by a heat exchanger, because you see, when it will come out, it will at a higher temperature and pressure compared to surrounding, and this will enter at atmospheric temperature and pressure. So basically we assume that we have a different heat exchanger which rejects heat q out, so that it will enter again at atmospheric conditions. Okay, so this is an assumption that we assumed. For analysis, we assume it is a closed cycle. And this closed cycle is called as Baraton or Joule cycle. Baraton or Joule cycle. So you see, we do not do any other analysis on this cycle. We all do all analysis, but practically it is used only 1%. Very less. In reality, most of the times we use this open cycle. Okay, but we do analysis for Baraton cycle, because we cannot do analysis on open cycles. Okay, so now, okay, so this is okay. Now Joule cycle, again there are 4 processes. What are the 4 processes? 1 to 2 is isentropic compression, you already aware of this, and 3 to 4 is expansion. Here heat addition and heat rejection are happening at constant pressure itself, constant pressure itself. Okay, so I don't think it will be very difficult to draw, okay, to draw TS and PV diagram here. Because TS and PV diagram are very important, otherwise you will not get an idea of the question. Okay, whenever you see a question, always try to draw at least one diagram, TS or PV. Mostly you draw TS diagram. Okay, but you need to know what is the TS and PV diagram, and you need to draw it, otherwise you will get confused with the points. Okay, now let's draw it. So 1 to 2 is isentropic compression, and I know that you know how to draw isentropic compression on PV diagram. Same thing, how we kept drawing it. Okay, so we'll start from here, we go like this. Okay, isentropic compression 1 to 2, then constant pressure heat addition, that also you know, it is a horizontal line, it is a horizontal line. So this is, let us say till here, so this is 3. Isentropic expansion, again you will come down. Mhm. Okay. So this is 3 to 4, and finally you will again do heat rejection at constant pressure. So again horizontal line, 4 to 1. Okay. So this is your work input, isentropic compression. This is constant pressure heat addition. This is work output isentropic. This is Q out constant pressure. Okay. Now you can do TS diagram also very easily. By this is your 1 to 2 process, isentropic. Okay, vertical 1 to 2. Then constant pressure, something like this, isentropic 2 to 3 4, and again 1 4 to 1. Okay. So here this is work input, this is constant pressure, Q in, work output, Q out, constant pressure. Pressure, remember, look, P2 is equals to P3 है and P1 is equals to P4. This you need to remember. Okay. So these are TS and PV diagrams for your Baraton cycle. Now how we can calculate the thermal efficiency? So thermal efficiency, we will use steady flow energy equation here. Steady flow energy equation. Now, do you have any doubt? I mean, anything, any confusion till now? No. So I give you one doubt. Tell me, when we used uh, Otto and diesel cycle, there also mass was entering, mass was leaving. Here also mass is entering. You see, here mass is entering and mass is going out. Mass is entering, mass is going out. Why are we taking open system steady flow here, and why did we use closed system equations there? Anyone? Any suggestion? Any idea? Anything? Yes, look, I told you know that where there we used heat transfer is equals to mcv dt, right? Where did we define that equation? In closed system, right? For constant pressure, we defined mcp dt, right? We defined those equations constant in constant vol in closed system, right? Here I am using steady flow energy equation. Here I am going to use steady flow energy equation. Okay, let's continue our discussion after we finish our analysis. Then maybe we will come back to this question. Okay, maybe it is too early for you. ठीक है, चलो. So again, what is efficiency? Tell me, what is efficiency of any cycle? Basically, is desired output upon heat supplied. So basically, this is your work input. This is Q supplied, constant pressure. This is work output. This is Q rejected. Again, constant pressure. Now, can I write it like this? Or should I tell you why I am writing like this? Is everyone okay with this statement? Yes, for cycle. Okay. Now, if you remember, what happens in heat exchanger? We talked about the application of steady flow energy equation in a heat exchanger. Okay. So if you remember, we talked about heat exchanger we assumed adiabatic. Okay, so our equation was H1 plus Q in is equals to H or H in H exit plus work output. Now in heat exchanger, we it's adiabatic or okay, no. Okay, so work output is zero. Work output is zero. Q supplied is equals to M HE minus HI. Okay, so I can say it is equals to M CP T exit minus T inlet, right? So similarly, I can write here for Q rejection and Q. Now do not get confused about the same formula we use for constant pressure there. If you go and cross check in closed system also, for constant pressure heat addition, heat transfer, we got the same formula, but that was just a coincidence. Okay, here we did not define anything MCV in, we did not define anything like this in steady flow. Okay, and this is different, and I'll tell you the reason in some time. Okay, chalo. So 1 minus Q supplied is M CP T3 minus T2 upon M CP T4 minus T1. Okay, so I can cancel this. 1 minus T1 by T2 T4 by T1 minus 1 upon T3 by T2 minus 1. Okay, so now I will not. Okay, okay, let's do it. I mean, I'm just repeating everything because the same thing we have done in auto cycle. Okay, now I'll take process 1 to 2 and I can write T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. Now, what is this P2 by P1? It is pressure ratio. Compression, what is happening in compressor? What is happening in compressor? In compressor, pressure is increasing. So we are taking RP is equals to P2 by P1. Pressure after compression divided by pressure before compression. Okay. So it is RP gamma minus 1 by gamma. Now 2 to 3, or 3 to 4. Process 3 to 4, I can say T3 by T4 is equals to P3 by P4 gamma minus 1 by gamma. Now you see this is constant pressure process. So P3 is equals to P2. So this is P2 and P4 is equals to P1 because constant pressure. Gamma minus 1 by gamma RP 1 minus 1 by gamma. So basically it is telling me that by A and B, T2 by T1 is equals to T3 by T4. Okay, and I can also write T4 by T1 minus 1 is equals to T3 by T2 minus 1. So basically I can cancel this, and efficiency I have gotten 1 minus T1 by T2. Okay, and I can also write this T1 by T2. What can I write? Where T1 by T2 is 1 upon RP gamma minus 1 by gamma. So it is equals to 1 minus 1 upon Rp gamma minus 1 by gamma. Okay. One thing also I can do here is, look, process 1 to 2, 1 to 2 is isentropic. So I can also write T2 by T1 is equals to V1 by V2 gamma minus 1. And I can, this is my compression ratio RV. volume before compression, volume after compression. Okay, gamma minus 1. So I can also write 1 upon RV gamma minus 1. So you can use any of the formula based upon what is given to you in question. Okay, so here RP is equals to pressure ratio, which is pressure after compression, pressure before compression, pressure ratio. And RV is compression ratio, which is volume before compression by volume after compression. Okay. Now there are few terms that you should know. First is back work ratio. So back work ratio is defined as work of compressor by work of turbine. Work of compressor by work of turbine. Okay. And mostly it ranges between 40 to 60%. 40 to 60%. Okay, wait. This one. Done? Okay. Okay. This is back work ratio. Now, if you know back work ratio, I think you can find out work ratio easily, which is net work on work turbine. So this is basically turbine work minus compressor work by turbine work. That also ranges in the same range, 40 to 60%. Okay. Next is specific fuel consumption. Specific fuel consumption. So basically, it is the fuel flow rate or mass flow rate of fuel, mass flow rate of fuel required to produce 1 kilowatt power output. Okay, so specific fuel consumption is mass flow rate of fuel required to produce 1 kilowatt of power. Okay, now what is power? Power is what? Work done per unit time. Okay, so mass flow rate of air into network. Okay, and also there is a term called air fuel ratio, which is mass flow rate of air upon mass flow rate of fuel. So basically now I can write mass flow rate of fuel by mass flow rate of air is this. Okay, so this is 1 upon air fuel ratio network. So this is kg per kilojoule or kg per kilowatt second. Okay. In terms of R also you can calculate specific fuel consumption. It is 3600 upon air fuel ratio net work. Okay. So you have to know one thing, that whenever we talk about heat transfer, you see, we are giving heat, so you will take mass of fuel into calorific value of fuel. But when you talk about work output or work net, then you talk about mass of air into network, small network. Okay, because this is giving you work, but mass of fuel is giving you heat. Okay, now, okay, and finally we have air rate. So this is also mass flow rate of air required to produce 1 kilowatt power output. Same thing you are going to do. Air rate is equals to mass flow rate of air by power, and this is mass flow rate of air into small work net 1 upon. This is basically kilo kg per kilojoule. If you want to find out kg per kilowatt second, if you want to find out kilowatt hour, then 3600 network kg per kilowatt hour. Okay, so very simple. Let us try to solve one or two questions on this quickly. Now, in a Baraton cycle, so whatever we have drawn that TS and PV diagram, it is Baraton cycle. Okay, air enters. Where will air enter? At what point air will enter? At what point air will enter? 1. Yes. So at 1 bar, 87 degree Celsius. Okay. So basically, what do we have? We have T1 is equals to 1 bar and T1 is equals to 27 degrees Celsius, or should I say 300 Kelvin, and pressure ratio RP. RP is what? P2 by P1 is equals to 5. I need to find out mass flow rate of air required to produce 600 kilowatt. So power is what? 600 kilowatt. Our output when the maximum temperature is which one? Can you see the diagram and tell me which one is maximum temperature? Yes, T3 is equals to 927 degrees Celsius or 1200 Kelvin. So basically they are asking calculate mass flow rate. Now what is mass flow rate? By net power is equals to mass flow rate of air into this network. Now in order to get 600 kilowatt of power, what is the mass flow rate of air? Okay. So I still don't know network. So I need to find out network first. Then only I will be able to find out mass flow rate of air. Now what is network? Network is work of turbine minus work of compressor. Yes. So this is, if you remember, we have also discussed our steady state equation, steady flow energy equation, that work of turbine is Cp dt, Cp dt. Okay, so T3 minus T4 minus Cp T2 minus T1. Okay, this is compressor, this is turbine. Okay, now look, Cp is same. Cp is given 1 kilojoule per kg, so I can write 600 by 1 T3 minus T4 minus T2 minus T1. Now, what do I know? I know, look, I know T1, I know T3, but I do not know T2 and T4. Can we able to find out T2 and T4? Yes, of course. What do we have? We can easily find out by using our Isent equation. So 1 to 2, I can say T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. Okay, so T2 is equals to 300 into 5, 0.4 by 1.4. T2 is equals to 475.14 Kelvin. Yes, same thing you can do with 4 to 1. It is again isentropic. So you can do T4 by T3 is equals to P4 by P3 gamma minus 1 by gamma. Okay, and you see P2 is equals to P3 and P4 is equals to P1. So it is P1 by P2 gamma minus 1 by gamma. That means 1 upon RP gamma minus 1 by gamma. Okay. So if you solve this, T4 you will get T3 into 1 by 5, 0.4 by 1.4, and T4 is 757.6 Kelvin. Okay, so now you can find out mass flow rate of air is equals to 600. This is already given to me. Then it is 757.6 T4. Okay, then T2 is I have calculated, and then T1 is 300. Okay, so once you solve this, 2.245 kg per second. Kg per second. So this is how this type of questions could be asked. Okay, let us see one more question here. An open cycle gas turbine uses a fuel of calorific value this. With air fuel ratio of 85, it develops a net power output of this. Determine the mass to 5 kilowatt hour of power output. Okay, 5 kilowatt hour of determine mass flow rate. Okay, so it's also simple. Okay, it's also simple. What you can do is calorific value is given, fuel air ratio is given. Okay, it develops a net power of this, net output of this. Okay, determine mass flow rate of air required to produce. Again, what is net power is equals to mass flow rate of air into network. Okay, so mass flow rate of air is equals to 5 kilowatt hour. 5 kilowatt hour of power output. Okay, so do you remember we talked about air rate? Air rate. So what was air rate? Air rate is equals to 3600 by network. Okay, so this is kg per kilowatt hour. Okay, now we need 5 kilowatt hour. Okay, so 5 into 3600 network kg per kilowatt hour. Okay, now this is given. This is given as work net is 130 kilojoule per kg. So 5 into 3600 upon 130. Okay, so can you calculate this? How much is this? So this is 138.46. 138.46, yes. Okay. Also, if they ask you to calculate efficiency, you can also calculate how? Network by heat supplied. Okay. Now I have already told you one thing. Network is calculated by mass flow rate of air and this, and heat supplied is calculated by mass flow rate of fuel into calorific value. Calorific value is the heat added when you burn 1 kg of fuel. Okay. So now what is this? Mass of air by mass of fuel. This is air fuel ratio and net work by calorific value. Okay. So air fuel ratio is given 85, net work is 130, and calorific value is 50,000. So basically it is 0.221 or 22.1% is your efficiency. Okay. Of course, when you read it in detail, I mean, I think you would have some specific subjects, topics as well. There you talk a lot about how to increase the efficiency, what is the effect of pressure or pressure ratio on the efficiency. All these things will be discussed in detail. Okay, but this is a brief introduction of this. Okay. Now, finally, let us go to the compressible fluid flow. Maybe 15-20 minutes more, and we will finish this. Okay. Now, what is fluid and what is compressible fluid? So, fluid, I think you already know. When you apply a shear stress, when you apply an infinitely small shear stress, if the body goes into deformation, it is called as fluid. Okay, so if it is a solid, if you know if it is solid and you apply a shear stress, it will not deform, it will not deform, undergo any deformation. Okay, but if it is a fluid and you apply a shear stress, its shape will deform like this. Okay, so now it has some angular displacement here. Its upper surface is moved a little further than its lower surface. You see, lower surfaces are less deformed than upper surface. Okay, so whenever you apply an infinite, even if you apply an infinitely small shear force, you still get a deformation. They are called as fluid. Now, when it is called incompressible or compressible, so it is called incompressible if its density does not change with a change in its pressure. So, if you apply some pressure and its density does not change, it is called as incompressible. But if you apply some pressure or even a little bit of pressure and its density changes and it has some significant change in the density, then it is called as compressible. It is called as compressible. Okay, so the basic principles that we use to define compressible flows are continuity equation, momentum equation, first law of thermodynamics, which is conservation of energy, of course, and entropy principle and equation of states. So equation of states are basically you have ideal gas equation, then we have real gas equations. Okay, so all these things comes in equation of states. Okay, now how do we define the velocity of pressure in a fluid, in a compressible fluid? How do we define the velocity of the pressure wave? Okay, so let us consider a one-dimensional flow through a long straight. So we have a rigid pipe. Okay, this is our pipe. Now we have filled it with fluid, which is compressible, and initially it is at rest. Now, when you move this piston, it will cause a disturbance. So, what will happen? Your molecules will feel a compression and expansion wave. Okay, compression and expansion wave. Okay, so they will come. First of all, look, these fluids that are the molecules that are here, they will push the molecules further. They will first of all go, collide with these other molecules and then push it further. So all the molecules will feel basically a compression and expansion force. Okay, and it is called as basically disturbance, and the disturbance in the fluid transmitted from one point to another. This molecule first of all will collide to another molecules, so compression will forces will apply, then it will move further and it will expand. So a combination of compression and expansion basically, which is a pressure wave, it is formed here. Okay, so the disturbance creates a pressure wave in the fluid, and the pressure wave moves with the velocity of sound wave in x direction, in x direction. So we have to calculate how, at what velocity it is moving, the pressure wave. Okay. So let us say V is the velocity of piston, C is the velocity of pressure wave. Okay. And which will be different. Which will be different. Okay. Now P is the fluid pressure in the pipe before piston movement, initial pressure. And D plus dP is the after piston movement. When the piston has moved slightly, when the piston has moved a distance x, the pressure is increased by dP. So the total pressure is P plus dP. Density rho is before the piston movement, rho plus dP is after the piston movement. dt is the small time interval in which piston moves the distance x. X is the distance traveled by the piston. So it is distance is equals to, oh, speed is equals to distance into time. Okay. So distance is equals to speed into time. And L is the total length, which is C into dt. Okay. Piston has moved till here only, but pressure has moved, pressure wave has moved from here till a wave point, till a wave point. Okay. So let us apply our conservation equations. So first continuity equation. What is continuity equation? By mass will remain same. Mass is not changing. Continuity equation is mass before compression. By continuity is because the continuity equation is conservation of mass. Okay. And mass after compression. Okay. So what is mass? Density into volume, right? Mass is density is equals to mass per unit volume. So mass is equals to density into volume. So density, volume is what? Area into L. After compression, density will change to this. Area will still remain same. Area is this cross-sectional area, okay? This cross-sectional area is area. And length is basically L minus X, okay? So L is what? L is C into dt. Rho plus d rho, area will be same, C into dt minus V into dt. Okay. Now let us divide by everything by a dt. So if dividing a into dt, the whole equation, you will get rho into C is equals to rho plus d rho C minus V. So rho C will get cancelled both the sides. Rho C. Okay, rho C will get cancelled both the sides, and what you actually get is C d rho is equals to rho V. Okay, and we will neglect here VDP, V d rho. Neglect V into d rho because it is small term. It is a very small term. Okay. Next is this. So this is your continuity equation. This is your continuity equation. Next is the second equation was momentum equation. Momentum conservation. Momentum equation. Okay. So rate of change of momentum is equals to net force. This is your Newton's momentum equation. Okay. Net force on the fluid. I know it could be a little boring, but I mean, I cannot do anything. They are very basic formulas. dV by dt. Mass flow rate into dV by dt. And force is pressure force. P plus dP area minus. So this is final pressure. This is initial pressure. Okay. So rho AL – this is mass into acceleration. Okay. This is mass. This is acceleration. So that is momentum. V minus 0, initial velocity, final minus initial velocity. dp into area. Okay. Write rho a v c dt by dt is equals to dpa, because here L is equals to C into dt. Okay. So dt and dt will get cancelled, and rho v is equals to dp by C. Okay. So now if we combine A and B equation, A equation and B equation, so what is A? Combining A and B, it is C d rho is equals to rho v, and this is rho v by dp c. Okay, so if you equating both, this and this is same. So c d rho is equals to dp by c. C square is equals to dp by d rho. So it is basically giving you the change in density with respect to change in pressure. C is equals to dp by d rho. So this is basically velocity of pressure or sound wave, whatever you want to call it, but it is in a fluid, in a fluid. Okay. What about in ideal gases? So this is in fluid. What about in gases? In gases, so what do we have? We have ideal gas equation for an isentropic process. PV gamma is equals to constant. So this is small v, and I can write density. I hope that you know that specific volume is basically equal to 1 upon density. Or do I need to define it? Are you okay with this, or do I need to define it? Now let me take log. So I can say dp taking log and then differentiating. So it is dp by p minus gamma d rho by rho is equals to 0. dp by d rho is equals to gamma p by rho, and earlier also we have defined c square is equals to dp by d rho, where pressure is equals to rho rt. Okay, so I can write c square is equals to gamma rt by p upon rho is equals to rt. Okay, so here I got c is equals to gamma rt. This is in ideal gas. This is in velocity of sound in ideal gas. Okay, so yeah, I think this is all. Basically, there is one more term which is called as Mach number. I think I forgot it. Mach number. It defines the ratio of actual velocity to sonic velocity. Actual velocity to sound velocity. Okay. And if Mach number is greater than 1, then you can say the flow is supersonic. If Mach number is less than 1, then the flow is subsonic. And if it is equals to 1, then the flow is sonic. Okay. And also it gives you a condition that if Mach number is less than 0.3, then only you consider the fluid, the flow or fluid is considered as incompressible. Okay, if it is greater, then it is compressible. Okay, so I know that we have covered a lot in this session. Okay, and of course, look, whatever topics we have covered today, it is a brief introduction of each and every topic. Auto cycle, I don't think you will need, but because I was told that it is in your syllabus, because in aerospace, I really don't think you are guys are going to study auto cycle or diesel cycle. But anyway, uh, but gas cycle, yes, in detail you are going to study, and it is a very big topic anyway. And even compressible flows, they are very big topic, but you will read them separately in detail. Okay, I have given you the basic introduction from thermodynamic point of view of all the cycles. Okay, and I hope by doing questions and all you would get gotten a good idea about the formulas. Of course, it is not enough, you have to do more and more questions. Okay, yeah, and believe me when I say, if you have learned whatever I have told in this session, auto cycle and diesel cycle, if you take gate questions, it will be much easier. Okay, I have taken a book question and it was very big, I know, but because it covered three or four concepts all together in that one question. Okay, in gate they will not ask you these many concepts all together. They will ask you maximum one or two concept. Okay, or they will break it into linked answer type question. Okay, in which you will get 4 marks question, 2 plus 2. Okay, so anyway, I think this is enough for today, and this is my last class. So if you have any doubt till whatever I have covered in any topic, whether it is first law, whether it is second law, entropy, Clausius, whatever it is, work transfer, heat transfer, feel free to connect with me. I don't know if you have my number or anything, but I think I can ask. You can ask Dinesh sir or anyone for my number. Okay. uh, I really don't think we are in the same group. Okay. Anyway, you can ask them my number, and if you have any doubt, just connect with me, or you can connect through the group. Okay. I'll ask Dinesh sir to add me into the group. Good. Cool. And before we end this topic, the whole subject, let me tell you one truth about thermodynamics. I don't know if you know that you understand the subject or you don't understand, but thermodynamics is a very confusing subject in the first when you study it the very first time. Okay, you may think that you understood things, but once you revise it the very first time, you will get very confused, and that's very common. That happens with everyone. Even it happened for me as well, and I know that it happens. But thermodynamics subject requires at least 3 revisions. Okay, so you revise it second time, you revise it third time, try to solve more and more questions, and I promise you it will get clear. But do not get frustrated the very first time, because it is a very confusing subject. So many formulas, so many concept, air, water, fluid, and all these things. Okay, all combined. So, and you don't know what formula you're going to apply at what condition. So of course you will get confused when you think you are going to apply this equation, but that equation you should not apply in that question. Okay, so it's very normal. Do not get frustrated. Just trust on the process, keep revising, and after 2 or 3 revisions, you will have a good idea on the subject. Okay, because I have already covered everything that is required in thermodynamics. I have given you summary. I have separated all the topics very, like very effectively. Otherwise, people don't even know what is first law of thermodynamics for closed system and what is first law of thermodynamics for open system. They do not even know that first law of thermodynamics for open system has 2 parts, steady and unsteady flow. Okay, trust me. So just keep revising. If you have any doubt, connect with me. Feel free to ask anything anytime. Okay, chalo. Let's say goodbye here, and I will see you some other time. Okay, thank you, Shubham, Jay, Amit. Okay, everyone. Thank you, Jay. Yeah, Kanish, bye. Thank you. I'm gonna disconnect now. So, okay.